Okay, so suppose that nobody in our class carries more than 10 pens. Yeah, sorry. Yeah. Mm-hmm. Oh, okay, sorry. So, suppose that nobody in our class carries more than 10 pens. There are 108 students in our class. How can you prove that there are at least 2 students in our class who carry the same number of pens? And actually, there is a lot more than 2 that do. For that, you could use something called the pigeonhole principle, which is a very, very useful rule for proving stuff. And here's what the pigeonhole principle says. Suppose you have n pigeons, and suppose you have n minus 1 places for them to roost. So for example, on this picture you got 5 pigeons, but there are only 4 places for them to sit. So then, unless some pigeons are out flying about, at least 2 pigeons will sit in the same roosting place in the same hole. In fact, the pigeonhole principle came from somewhere which, as far as I know, had nothing to do with pigeons or holes, but it's just such an interesting image of pigeons sitting in their holes that everybody's talking about pigeons and holes ever since, rather than pigeonholes where you could put 1 or more letters. Okay, so how do we apply this principle to our problem? So we have 11 possible number of pens. Somebody may have none, somebody may have 1 or 2 or 3, up to 10. So if our pigeons are students and our numbers of pens correspond to pigeonholes where pigeons roost, then even with 12 people in our class, there would be 2 who would have the same number of pens. And here is why. Suppose that nobody in our class has the same number of pens. Well, one person has 0 pens, and another one has 1, and another one has 2. How many different people we can have like that? Well, 11. So even if we have just 12 people, there would be 2 who have the same number of pens. By the way, we have no idea what that number is. It may be that there are 2 people who have none. There may be 2 people with 3. We have no idea. We just know that there are at least 2 that have the same number. And you could make the same argument to say that there are at least 10 that have the same number. Because if it were less than 10, let's say 9 for each scenario, we would have 101 kind of people total if we sum up people with 9 people with 0 pens, 9 people with 1, and all the way to 9 people with 10. But wait a moment, we have 108, and it's more than 101. Again, we have no idea who those people are, and we have no idea what is that magic number of pens that a lot of people have. We just know that it exists. So in the pigeonhole principle, it's possible that some of the pigeonholes are empty. So maybe nobody in our class has 5 pens. People have either less or more. Nevertheless, at least one hole should have more than 1 pigeon. So for example, in this picture, 2 holes in the top row has 2 pigeons each, and 1 hole at the bottom has nothing. It doesn't really change our argument. It kind of makes it even stronger. We have even more people who have same number of pens. And the pigeonhole principle in general works whenever you have more people than pens, more pigeons than holes. It's a very, very common principle which people use in proof of all sorts of things. But why am I bringing it up when we are talking about natural deduction and resolution, other than the fact that that's yet another way of proving things, yet another rule we could use? Here's an interesting thing. We could write the pigeonhole principle as a tautology. That's not that hard to do. But we can prove that resolution proofs of the pigeonhole principle would be really, really big. If the only rule we use is resolution, then really we might as well write a truth table. The proof that we would do with resolution would be kind of the same order of magnitude as a proof, as a truth table, which tells us that that's not probably the best way of proving stuff. But surprisingly enough, that's the one that seems to be working best in practice. We don't know how to make natural deduction systems, even when we know that there are small natural deduction proofs. You could figure out things with natural deduction, but somehow we still don't understand it well enough to program, to make systems that would do things for us. And the problem is that this kind of reasoning generally does not involve counting. The moment you could count, you could prove more stuff. You could prove pigeonhole principle, and you could prove things that follow from pigeonhole principle.